Hi, this is Shahbaz Masih. I hope you guys are keeping yourself safe in this COVID-19 era. Today, I will talk about my Capstone project presentation. It's for IBM Coursera Advanced Data Science Specialization, and it's about predicting power output of a combined cycle power plant by using machine learning, deep learning, and big data tools. I will take you step by step from a simple linear regression model to decision tree regressor and a little bit more advanced random forest regressor. And then I will move on to deep learning tool neural network. This presentation consists of two parts. The first part is the business presentation for stakeholders. I will talk about the use case uh, by giving you some business understanding, what's the business problem, and what data set I used to solve the business problem. And then I'll show you the solution that's proposed to solve the business problem, which is a correlation to predict power output of the combined cycle power plant, and then the report that I have generated for the whole project. The second part of the presentation is data science presentation, and it's for data scientists. I will show you what architectural choices I made, and then how data was explored and its quality was assessed, and then how it was pre-processed and transformed before we delved into feature engineering. And then I'll talk about how feature engineering, which is an important component, it was accomplished by using correlation metrics. Then what model performance indicators were used, what was their justification, and then I'll show you my code for model algorithm. Okay, let's start with the first part of the presentation, that is the business presentation for stakeholders. For business understanding purposes, we will start with an introduction of a combined cycle power plant, or a CCPP. A CCPP consists of a gas turbine, a heat recovery steam generator, and a steam turbine. In a CCPP, the electricity is generated by gas and steam turbines, which are combined in a single cycle. Fuel burns at the gas turbine, makes the turbine blade spinning and driving electricity generator. The exhaust heat from gas turbine is captured by heat recovery steam generator. The heat recovery steam generator generates steam from this exhaust heat and delivers it to the steam turbine. The steam turbine uses this steam to generate additional electricity by driving an electricity generator. Gas turbine load is sensitive to the ambient conditions, for example, temperature and pressure and relative humidity. And steam turbine load is sensitive to the exhaust steam pressure or vacuum pressure. Also, for business understanding purposes, we will look at how does a power grid work. Here is a real-world example of California power grid for demand forecast and actual demand for power on hourly time scale within a day. Also, power is supplied by the grid from multiple resources to meet the demand, and contribution from each source changes with time. You can see there are multiple resources, and also the contribution is changing for each resource within a day. For example, for renewables, in the early part of the day they are contributing less, but later part of the day they are contributing a lot more to the percentage of the power supplied by the grid. From the discussion so far, we can gather that power generation is a complex process. Understanding and predicting power output is an important element in managing a plant and its contribution to the power grid. The operators of a regional power grid forecast power demand based on historical data. Then they compare the forecast against power supply from available resources, for example, coal, natural gas, nuclear, solar, wind, hydro, or a CCPP. Power generation technologies, for example, solar and wind, are highly dependent on environmental conditions. Also, power generation technologies are subject to planned and unplanned maintenances. The challenge for a power grid operator is to manage a shortfall in available resources versus actual demand for power. Therefore, it is extremely vital to forecast power supply from available resources. Predicting the electricity generated hourly based on ambient variables enables to evaluate whether the generated power will be sufficient to meet the growing consumer demands. Proactive steps to address the demands can be taken if the forecasted power is found to be insufficient. For example, build more power plants. This process can take many years or even decades of planning and construction. Or power can be bought and imported from other regional power grids. This choice can also be very expensive. Or small peaker power plants can be turned on. In this project, the power generated by SECPP will be forecasted by using ambient condition data of temperature, pressure, relative humidity, and exhaust vacuum pressure. The machine learning models, regression models, and neural network will be used to develop a correlation, and also a report will be written to be handed over to the client. The data was downloaded from a UCI machine learning repository. The link is given below. It had a total of 9,568 records. The forecast based on ambient condition data will help better management of power supply to meet the consumer demand. It will also help take the most viable option economically to meet the consumer demand. For example, build more power plants, or buy power from other grids, or turn on peakers. It will also help better management of power shortfalls from other sources of power supply due to planned and unplanned maintenances and inconsistent environmental conditions in case of solar and wind plants. In order to find the solution, PySpark ML library was used to run regression models. There were three types of regression models that were run: linear regression models, random forest regressor, and decision tree regressor. Different number of input parameters were used as features. In some cases, all four parameters were used as input features. In other cases, three, and in some cases, two. This decision was based on the correlation metrics that was used, and I will explain it in the next section. Only in case of a linear regression, hyperparameter tuning was not done for one set of cases. In all other cases, hyperparameter tuning was done by using grid search method. And here you can see from the results that random forest regressor gave us the best result in terms of R squared. Also, in order to find the solution, neural network modeling was done. Kera's open source library was used, and it was run on top of TensorFlow. And in this case, you can also see models were run with different number of input features. For model optimization purposes or tuning purposes, different number of hidden layers were used. Two types of loss functions, MSE and MAPE, were used. Different learning rates were tried, and also different number of epochs based on the learning rate were used. And in this case, you can see that with the four number of input parameters and with the mean square error as a loss function and a learning rate of 0.0001, the R squared value of 0.929 was achieved, and that was the best result. Since the best results were achieved with the regression models, so a correlation was developed after calculating the weights for each parameter, And you can see that now the plant power output can be forecasted by using input parameters of temperature, pressure, exhaust vacuum, and relative humidity. And the next deliverable that was promised to the client was a report, and that's what I will show you next. So here is the project report of the combined cycle power plant power output prediction. And I started with the introduction by giving business understanding and background first. And I've explained it already. And then where does a power plant like CCPP stand in the whole scheme of things in power grid, and why it's important to forecast its power output. And I mentioned the business case and the use case. And then data was looked at. And then I moved on to the methodology. And first thing was exploring the data. And simple statistics were looked at, like max, minimum, quartiles, standard deviation, mean, and total number of values. And then box plots were used to see if there are any outliers. And you can see that there were some outliers there. Then Seaborn library was used to look at these plots of each parameter against the power output and also the parameters against each other, just to find out the relationships, and that will help in feature engineering. And I will explain everything in the next section, the data science section. Then data was cleaned. It was looked at for zero values or null values, if they existed or not. Then the column names were changed to be more representative of the data. Then relative humidity value was investigated for values higher than 100%. And it was cleaned off the outliers by using Z-score method and IQR score method. And IQR score method performed better, and it removed more outliers. So the data filtered by the IQR score method was chosen for further analysis. Then feature engineering was looked at based on the correlation metrics, correlation coefficients. And then what kind of models were used and how they were built. That process is explained here. And then neural network architecture was also discussed, and then how the neural network model was diagnosed and tuned for the learning rate by using loss curve. That process is explained here. Then why was R-square chosen as the model performance indicator? That's discussed here. Then results of both regression modeling and neural network were discussed, and the whole project was concluded and references were mentioned. Now we'll move to the data science part of the presentation. It's mainly for data scientists, and it's a little bit more technical. Here is a brief overview of the tools that were used for architectural choices. IBM Watson Studio and Jupyter Notebooks were used for all kinds of coding, for data exploration and wrangling and transforming, and all the modeling was done on the Jupyter Notebooks as well. IBM Cloud Object Storage was used. Firstly, the data was retrieved from an online repository, and then it was placed on IBM Cloud Object Storage. And after the data was cleaned and transformed, then it was placed on Apache Spark for further analysis and modeling. For data exploration, visualization, and transformation, mainly PySpark, Spark SQL, Seaborn, Matplotlib, scikit-learn, and Pandas data frame libraries were used. And for feature engineering, modeling and evaluation, it was mainly Spark ML library, uh, Keras deep learning library, NumPy, and again scikit-learn were used in that section. The basic statistics were looked at for data exploration purposes, and you can see that the results show that relative humidity and plant power output have the highest standard deviation. Relative humidity depends upon pressure and temperature, and therefore has high standard deviation, which means it's more widely spread out than both temperature and pressure individually. The high standard deviation of power output also shows its high variability, indicating the impact of variation of ambient conditions on power output. However, maximum value is only around 10% higher than the mean value, unlike relative humidity, exhaust vacuum, and ambient temperature. Atmospheric pressure has low standard deviation and indicates low variability because atmospheric pressure does not change much generally. Having curiosity about the data is very important for any data scientist. So the data was looked at normal values and relative humidity, which generally does not exceed 100%. Some values were found greater than 100%. It was actually 55 records that had relative humidity values more than 100%. So it was further investigated if those values were correct or not. So the relative humidity definition was looked at, which is the amount of water present in air expressed as a percentage of the amount needed for saturation at the same temperature. And there is a chance that supersaturated air might contain more water than vapor. So relative humidity can go above 100%. So these values, which were greater than 100%, were not removed from the data. For further data quality assessment, null values were looked at, no null or missing values were found, and there were also no zero values. For further data quality assessment, box plots were plotted, and you can see that atmospheric pressure had almost normal distribution around the median value, and it had almost zero skewness, you can say that, while all other parameters had some kind of skewness attached to their data. Also, box plots revealed that there are outliers present in atmospheric pressure and also in relative humidity. You can see that this is the presence of the outliers indicated by red circles in relative humidity and atmospheric pressure. For further data exploration purposes, scatter plots were plotted by using a seaborne library, and here you can see that atmospheric temperature and exhaust vacuum had a stronger linear correlation with the plant power output than the atmospheric pressure and relative humidity. Also, atmospheric temperature and exhaust vacuum had a linear correlation. All these observations hint towards the need of feature engineering when we will move to the modeling step. After data exploration, data was transformed for further analysis. Since no null values or zero values were found in the data, so no action was needed on that front. Also, relative humidity values greater than 100% were found to be valid, so they were not removed from the data. Column names were changed to be more representative of the data. For example, RH column was changed to rel humidity. Since box plots revealed that there is a presence of outliers in the data, so Z-score method and IQR score method were used to filter the data from the outliers. Z-score method removed 58 records from the data, And IQR score method removed 100 records from the data. And in the next slide, we will show how it worked out. Z-score is defined as the data point minus the mean of the population divided by the standard deviation of the population. So in other words, you can say that Z-score of a data point is how many standard deviation that data point is away from the mean. Usually a threshold value of 3 or minus 3 is used as a cutoff for filtering the data, and that's what we used as well. And you can see that the outliers numbers was reduced significantly after using the Z-score filter. The second method that was used to remove the outliers from the data was IQR score method or interquartile range score method, and that range is defined by this formula where Q1 and Q3 represent first and third quartiles respectively. And you can see that from relative humidity, the IQR score method removed all the outliers. There is no outliers present in relative humidity after filtering the data. And then also in the atmospheric pressure, the number of outliers that was removed after applying the IQR score filter was much lower than after applying the Z-score filter. So therefore, the data filtered by IQR score method was further used for modeling and evaluation purposes. As mentioned earlier, scatter plots, they hinted towards the need for feature engineering, and for that purpose correlation coefficients were looked at. And here you can see that atmospheric temperature and exhaust vacuum, they correlate with the power output of the plant much stronger than the other two parameters. Also, atmospheric pressure correlates with the power output a lot stronger than the relative humidity. So you can see that this strong correlation hints at two independent variables to be used as input features. Then the difference also lies between atmospheric pressure and relative humidity, and so that points towards maybe 3 number of input parameters as features, and also the correlation number of 0.398 is not a very small number for relative humidity. So that points towards maybe there should be all 4 parameters to be used as input features. So 4, 3, and 2 features were used as input to estimate the output. After data was transformed by using Pandas data library, it was loaded onto Apache Spark. For all the regression modeling purposes, Spark ML library was used, and the first step was building a pipeline. For that, a vector assembler was used. A vector assembler is just a transformer that combines a given set of columns into a single vector column. It is passed the number of features that's already explained in the feature engineering section. It was 4, 3, and 2. And then linear regression model was built by passing a label column, which is the power output column of the data set. Then it was passed features column that's generated by the vector assembler. And then it was also passed the prediction column, which is a newly generated column. It is the forecast for the plant power output. It was also passed the model parameters, for example, the maximum number of iterations, regularization parameter, which is a trade-off between the loss and the overfitting, and also elastic net parameter. After loading the dataset onto Apache Spark, it was split into testing dataset and training dataset. The testing dataset was passed to the model for training purposes, and the number of iterations, regularization parameter, and elastic net parameter were tuned for optimization purposes. And then for every run, the model was evaluated by using R squared, and for the best value of R squared, the weights of each input parameter were calculated, and also the intercept was calculated, and a correlation or equation was developed to forecast the plant power output. A hyperparameter is a parameter that is external to the model. In Spark ML, hyperparameter tuning can be done by using a cross validator. Cross validator is passed three parameters. First one is called estimator. It can be either an algorithm or a pipeline, but in our case it's a pipeline that we have already built. Then it's passed a set of parameters, which is a parameter map. It's also called parameter grid, and the model will choose parameters from within that grid. The third parameter it is passed is called evaluator. It's a metric for model performance. So the way cross-validator works is it divides the data into divisions equal to number of folds. For example, if there are 3 folds, then it will divide the data into 3 divisions. If we assume that those divisions are called first division, second division, and third division, then in the first run, what it will do, it will take first division and second division and use them as a training data set and use the third division as the validation data set. Then for the next run, it will use first division and third division as the training data set and the second division as a validation data set, and so on. And when it computes the average evaluation metric, it does the average for all the folds. The second type of model that was built for regression was random forest regressor. The way random forest regressor works is it divides the data into subsets of decision trees. So there are a lot more parameters to tune, and also these subsets of decision trees, they are executed in parallel. So it becomes a lot more powerful because there are a lot more parameters and features for this kind of models. So there is a chance it might overfit and might not perform as good for the testing data set. The process for building this kind of model is the same as a linear regression model. We build a pipeline first by using a vector assembler, as explained in the linear regression model section. Then because it's a different kind of model, so different parameters are passed to the model. For example, a number of trees. Increasing the number of trees will decrease the variance in predictions, and that improves the model's performance and its test time accuracy. The second parameter that it is passed is maximum depth. Increasing the depth makes the model more expressive and more powerful. It takes longer to train, and because it becomes a lot more cautious and more powerful, so it might overfit as well. There's a chance of that happening. In linear regression modeling, the hyperparameter tuning was done after running the model. But in case of a random forest regressor model, hyperparameter tuning was made part of the model. So again, cross-validator was used. It was passed the pipeline, the parameter grid, and the model itself, just as in case of linear regression. And then the model was tuned for number of trees and maximum depths. And for every run of the model, R squared was calculated to evaluate the performance. The third type of regression models that were built by using Spark ML were decision tree regressor models. Unlike random forest regressor models that divided the data into subsets, here the model was built on entire data set, and it uses all the features and variables of interest at the same time, which was not the case in case of a random forest regressor, because it divided all the features also into subsets. So how decision tree regressor model was built was the same process as the random forest regressor process. There was a pipeline that was built first by using vector assembler, by passing the features to it. And then the decision tree regression model was built by passing different parameters like randomness of the data and maximum bins. Maximum bins, it lets the model to consider more split candidates, and it makes fine-grained split decisions. And the maximum bin is always less than the total number of instances. Just like a random forest regressor model, hyperparameter tuning by using a cross-validator was also done in decision tree regressor by passing it into the model already. And then the model was tuned for maximum number of bins and evaluated by using a R squared method, and the same process was repeated for every kind of model or the run. Next I moved on to deep learning. Kera's deep learning library was used to build a neural network. A neural network is a combination of layers of neurons stacked together to form a bigger architecture. There are three types of layers in a neural network. An input layer that consists of input parameters. In our case, it will be 4 input parameters or 3 input parameters or 2 input parameters I discussed earlier. Then there is an output layer that spits out the output, and in our project it will be the forecasted power output of the plant. Then the third types of layers in a neural network are hidden layers. The number of hidden layers and the number of neurons in the hidden layers is not fixed. It is decided by the optimization or tuning of the model. Each neuron has its own weights for parameters when it moves from one layer to the next, and it's actually targeting a certain or minimum loss function, and to give us maximum accuracy. The types of loss functions are mean squared error or mean absolute percent error, etc. The advantage a neural network has over regression is that feature engineering is kind of automated, because the number of features and their weights, they are decided during the running of the model itself. So feature engineering is kind of automated. The second advantage it has over regression is the non-linearity of the features is captured, unlike regression models. Neural network architecture is shown in this diagram with the 4 input features and 3 hidden layers and 1 output layer. As you can see that if there are 4 input features, then all the features are there. But if there are only 3 features as input, then ambient temperature, exhaust vacuum, and atmospheric pressure were chosen as input features. If there are only 2, then it's only ambient temperature and exhaust vacuum, as we mentioned in the feature engineering section. Then there are 3 hidden layers. First layer has 8 neurons, and it had rectified linear unit activation. This activation was chosen because it's just the beginning of the data analysis, and we are not sure whether linearity is there or how much linearity is there in the data. So therefore, rectified linear unit activation was chosen. Same thing in the second layer, rectified linear unit, and also in the third layer, rectified linear unit activation was chosen. But number of neurons were different in second layer. It was chosen to be 6. Then in the third layer, it was 4. Then in the output layer, because there is only one output parameter, that's the power output, forecasted power output of the plant, and so there was only one neuron chosen. And here is the linear activation, because now we know that we want the result in the form of a linear correlation. If there are 3 hidden layers chosen in the model, then all these 3 layers were used. If there were only 2 layers chosen for the model, then first 2 layers were chosen. And if there was only 1 layer, then only the first layer was chosen to be part of the model. And yeah, that's it, I think, about the architecture of the model. As already explained, the number of input features were 4, 3, and 2 parameters. Then the number of output features was only 1. We were forecasting power output of the power plant. Then there were 3 number of hidden layers, and in different cases 1, 2, or 3 layers were used. Then activation in the hidden layers was set to be rectified linear unit, because linearity of the data was not assured. Then activation in the output layer was set to be linear, because we have to get output as a linear correlation. Then number of epochs was set to 100 and 200 depending on the learning rate. An epoch is one full cycle of the whole data set through the model. So if the learning rate is low, that is the rate at which the model adapts, then to reach the desired loss or accuracy, we need more epochs. So the lower the learning rate, the more epochs were used. There are different type of optimizers in the Keras library, but Adam was chosen. An optimizer is kind of an algorithm that decides how the weights change to reach a desired loss or desired accuracy. Loss function is just a measure for success. It can be mean squared error, or it can be mean absolute percent error. And these two were used as loss functions. Learning rate, again, this is just the rate at which the model can adapt, and it was set at 5 different values just to try what is the optimum number. It was set to 0.1, 0.01, 0.001, and so on. Batch size was set to 8. Batch size decides how the data will be divided into equal number of sizes. For example, if the data has 100 number of records and the batch size is 5, then there will be 20 records in each data set. Okay. A neural network has several learnable parameters. Therefore, training a neural network is a challenging task. The analysis of how one parameter affects other parameters, or how it impacts the training process, is almost impossible. But luckily, there are tools available that can help us to know if the training is moving in the right direction. For example, after every epoch, the loss function should be reduced or accuracy should improve. And there are tools like that which can tell us. For example, those tools are loss curve, uncertainty curve, or accuracy curve. We'll talk about the loss curve and how it can help us diagnose the learning rate for the model. The learning rate is actually the step size that the model takes at each iteration for reducing the loss function, or it controls how quickly the model is adapted to the problem. If the learning rate is too low, then it might take a long time for the model to run, and sometimes it makes it difficult for the model to converge or to reduce the loss function. And if the rate is too high, then optimum loss or accuracy might never be achieved. Kara's Adam optimizer that was used as an optimizer in the neural network modeling, it has a default learning rate of 0.001, and so we will use the loss curve diagnostics to see if this default learning rate is correct or not. So what is a loss curve? It's just loss plotted against the number of epoch. And as you can see, if the learning rate is too high, model will never converge to the desired outcome. It's indicated by this curve. And if the learning rate is high, again the model will never reach the desired outcome or the desired loss. It will just continue moving in the direction without touching the optimum point. If the learning rate is too low, represented by this blue line, you can see that the model will take a long time to run, so you have to increase the number of epochs. And also, it will be very slow to converge to the desired outcome, and that's also not desirable. A good learning rate is indicated by the curve indicated by this red line, that the model gradually keeps converging to the minimum loss until it reaches stable minimum loss. So to decide how our model performed, we have plotted the loss against the epoch, and this is the case with the 4 features and 1 hidden layer, and you can see that it resembles more closely with the high learning rate. But you can never for sure say that until you have seen all the cases of higher and lower learning rates. So this model used the Adam's default learning rate of 0.001. So the runs were made with learning rate of lower learning rate than 0.001, for example with 0.0001, or with the higher learning rate like 0.1. So for single hidden layer models, loss was plotted against epoch for different learning rates. And here you can see that this purple line is indicating that this learning rate is too low. It's taking a long time for the model to converge, and we are nowhere close to the optimum loss even after running for 200 apex. On the other side, to decide about the other learning rates, which one is the optimum, so this part of the model was enlarged on the right side, and here you can see that the green line, which is indicative of a learning rate of 0.001, it's converging with a better accuracy than the learning rate of 0.01 or zero point 0.1. So the red line that is indicating learning rate of 0.001, it's slow to converge, and also it's converging to a minimum loss, but the minimum loss of learning rate of 0.001 and 0.0001, they look almost the same. So the next set of runs will be run with both these learning rates to decide about the optimum. It will be 0.001 and 0.0001. Here loss curve was plotted for different number of hidden layers, one hidden layer, two hidden layers, and three hidden layers. And to decide about the optimum learning rate, this part of the model again was enlarged and looked at, and here you can see that the brown line, the red line, and the orange line, they converge better. And from here you can see that the orange line, the red line, and the brown line, they all belong to learning rate of 0.0001. So that was considered to be optimum in case of 4 features. Now we will talk about why was R-squared chosen as a model performance indicator. So the whole objective of this project is to forecast power output of a plant based on environmental conditions data. So it's a regression problem. To solve a regression problem, you can either draw a best fit line, or you can calculate this line by using algorithms. So the better the scatter around that best fit line, the better the regression model is. R-squared, it actually calculates that scatter around the fitted line. So therefore R-squared was chosen as the model performance indicator for all these regression models that we have used. R-squared can be calculated by the formula given here. You can see that it is actually just a ratio of the variance explained by the model to the total variance. So the higher the value of R-squared or closer to 1, the better the model performance is. It's only very few cases which are like very difficult to regress or very difficult to forecast. For example, human behavior, where even low value of R-squared can give us a good enough estimate. In this figure below, here the R-squared value is 0.15 and here it's 0.85, and you can see that with the 0.85 value, the scatter around the fitted line is a lot less and the model looks a lot better. It will generate very good results for prediction. The learning rate is actually the
Now I
step size
will
that the
show you
model
my code.
takes at
I will
each
only show
iteration
the first set of
for
runs. with
reducing
linear
the loss
regression,
function.
how to build
Or it
pipeline,
controls
how to
how quickly the
train
model
the
is
model,
adapted to the
and
problem.
then how
If the
to come
learning
up
rate is
with the
too low,
correlation from the
then
results,
it might take
then how to do hyperparameter tuning, and
a
again
long time for the model
run
to
the
run,
models and
and sometimes it
come up
makes
with
it
the
difficult
results.
for the model to converge or
The other
to
types of models,
reduce the
they
loss function.
uh,
And if
take
the
longer
rate
time
is
to
too
run.
high,
So I will display
then
only one set of
optimum
runs
loss or
and
accuracy
just
might
show the
never be
code for
achieved.
all other kinds of runs, including
Whereas
neural
add-on
network.
optimizer
Okay,
that was used as an optimizer in
here you can see that
the neural
I'm
network
already at
modeling,
the
which
stage
has
where
a
a linear
default learning
regression
rate
model
of
is about to be built.
0.001.
So the first step
And
is creating a
so we
pipeline.
will
So
use the
here you
loss
can
curve
see that we
diagnostics
used
to see if
PySpark
this
ML library,
default learning
and
rate is
now we're using vector
correct or not.
assembler to transform input parameters into features vector. Here you can see that the feature vector is passed 4 parameters here, then 3 parameters here, and 2 parameters here for feature engineering. And in the next step, the linear regression model was built, and it is past the prediction column, which is the forecast for power output, then label column, which is the power output column, and then the features column that we created by vector assembler. And then it was passed the linear regression parameters, which is maximum iteration, regularization parameter, and elastic net parameter. And that pipeline was then passed the vector assembler and the model. So in the next step, the model is trained, and you can see that it's passed the training data set. And we did it for all the models with 3 parameters and 2 parameters as well. Then how we created equation after running these models and training them. So we just used a loop between weights and the input features column, input features columns names, and it just got the weights from here, from the model, and the names of the columns were also iterated by using this loop, and then this equation was spit out. So now I will run all these code lines just to display one set of code. So here you can see that now the pipelines are created. And then the models are set up. And then here the model is being trained with the 4 parameters as input features. Since it's linear regression, so it doesn't take too long. Yeah, so it's already run. And the same thing with 3 and 2 parameters, since I will show only for 4 input features the equation process. So that's all what we needed to run. And here you can see that it generated the equation from the weights and the columns name by using this loop command. So I will not show the running of any more code because that's all the process there is. Same thing was done with the 3 input features. The correlation was built, and then with 2 input features, you can see that only exhaust vacuum here, and the atmospheric temperature were used for two input features. Then the model were tested with this testing dataset, and the R-squared numbers, they were calculated. So we should run this code with the 4 input features. And now here with 4 input features, we will calculate the R-squared values. So here the R-squared value with the training dataset and with the testing dataset. Okay, then hyperparameter tuning was done for the linear regression model, and you can see that again we are using PySpark ML library, and now we have to set up cross validator, and we will pass param grid builder to it. Okay, I will show you step by step. So cross validator, it was passed the estimator, the evaluator, and the number of folds, and then parameter grid was built for grid search, and cross validator was passed the parameter grid, and we did it for all kinds of number of input features, for 3 input features and for 2 input features as well. Then the model was trained again by passing the training dataset, and then it was tested with the testing dataset for 4 input features, and then for 3 input features, and then for 2 input features. And again, these R-squared values were calculated for all cases, and these are the results. So in the same way that I have explained in the presentation already, the models were set up, equations were built, and for random forest regressor, the only difference was the model type, because here model type is random forest regressor. We passed the similar kind of features, similar kind of labels, and then features column, prediction column, and label column. But these parameters were different because now it's a different kind of model, so we have to pass maximum depth and number of trees here. And those are the parameters we actually I actually tuned as well. Then again, those pipelines were passed the vectorizer, vector assembler, and the model. And in the same way, cross validator was set up. This time without running the model first. Cross validator is already included, and it's a part of the model. And again, parameter grid was passed to the cross validator, and the model was trained with the training data set, and then R-squared was calculated. Okay. And same thing with the decision tree regressor. Again, it's a different kind of model. So the first 3 parameters are the same, which is the label column, prediction column, and features column. But then this is a different column. We had to pass maximum number of bins, and this parameter was optimized by running the model number of times and calculating R-squared value. Okay, and then again the cross validator was set up by passing the pipelines and grid parameter grid builder, and then grid builder parameter grid was passed to the cross validator, and then the model was trained by using the training data set, and then tested with the testing data set, and then R-squared values were calculated. And now we moved on to the neural network section. And here you can see that now for the training data set with 4 parameters as input features, we created a training data set. And then for testing data set, it's for X, it's only the input features, and for Y, it's the output feature, power output. And again, for the test data set, we created, split it into X and Y variables. And X is the input data set, which is independent variables, and Y is the dependent variable, that's the power output. And then you can see that Keras library was used, and it was built on top of TensorFlow. And here Keras model was set up. It was a sequential model. And then it was given the input layer, that's the input layer code. Here 4 features were passed, and batch normalization was included here. Then the first hidden layer, it has 8 neurons and activation of rectified linear unit. And then similarly, although they are not being used here, but that's the second layer code. Here the second layer code with the 6 neurons, and again the same activation of ReLU. And then the third layer, it's not being used here, but the code is here. And then that's the output layer code with the activation of linear. And it's only 1 neuron, because there is only 1 output parameter. And then model was set up with the optimizer Adam, and then loss was set up as MSE. And later on we tried the MAPE loss as well, so that's why we had to set it up here. Then the model was trained, and you can see that it's giving the performance with every epoch. This is the 17th epoch out of the 100 epochs that we have set, and showing the loss function here. This is for the training data set, this is for the testing data set. And again, because we also had to diagnose it, so we plotted the plots here for the loss curve. This is the code for that. And then R squared was calculated for training data set and the testing data set. Okay. And now we moved on to, earlier we were using only 1 hidden layer, and now it's 4 variables and 2 hidden layers. So you can see that now the second hidden layer code is also activated. And similarly, different sensitivities were run with different number of hidden layers, different loss functions, and different learning rates. That's the part that I will show you next. So here you can see that we are building the model loss curve after every run. And now the diagnostics were run by using different learning rates. We started with the learning rate of 0.1, and then moved on to learning rate of 0.01, and then learning rate of 0.0001. And where it's set up is it's in the optimizer. So here you can see that we set up Adam, but instead of default learning rate, we set it to be 0.0001. The default is 0.001. And then we pass that optimizer to the model here. And then with different learning rates, this plot was generated to make a call, what is the optimum learning rate. And then the same plot was enlarged by using the code, by selecting a different scale here and using matplotlib library. And here you can see that the learning rate of 0.001 and 0.0001 performed the best, as I already discussed. And then learning rate with the different number of hidden layers. That code was set up and run. And then neural network models with 2 parameters as input features. So now those cases were run. And then with only 3 parameters as input features. So that case was run here. And then we investigated a different loss function with 2 variables and with 3 variables. And those run results are also discussed in the previous part of the presentation. So here you can see that the loss function is set up to be mean absolute percentage error instead of MSE. The other architecture of the neural network was the same. Okay, that's all that I have to show about my code. Thank you.
Now I will just sum everything up what was accomplished in this project. Firstly, the business problem in the use case were identified and required data was discussed. And then the data was pre-processed for analysis by data exploration and transformation. And then for feature engineering, exploratory data analysis and correlation recognition were used. Then machine learning and deep learning models were used to solve the business problem. And then results of the project were discussed and a solution to the business problem was presented in the first part of the presentation. Thank you very much for listening to this presentation. If you have any questions, please mention them in the comments section below, and I will get back to you. Also, the link to the GitHub repository is also given. Okay, thank you.